Hello class, welcome to our Combinatorics lecture for Wednesday, April 15th. However, I'm recording this lecture on Thursday, April 16th. Um, so I am behind, as I mentioned I might be. I'm sorry for that delay, but as I also mentioned, I've been busy grading tests, so that has thrown me off of my schedule a little bit. However, the good news is your tests are all graded, right? So, and I have emailed those back to you a couple of days ago, so you've got your test grades back, and so the grade book in Blackboard is pretty much up to date, except for homework 5, which you have submitted. Which I have not graded yet. However, the answers to homework 5 are posted. Um, I have not posted the answers to the test yet, though, so I will eventually post the answers to test number 2. Um, there's another homework posted, also homework 6, about inclusion, exclusion. I hope that is not too lengthy a homework. I tried to cut it down some, but still keep enough problems there to give you practice with inclusion, exclusion. I know some of them are going to be lengthy and some will be more logically challenging than others. Um, that homework, I believe, is due on, I think I put April 24th, correct, which is Friday of next week. I will post a homework 7. However, and so that's to help you with to prepare for our last test, which will be on Monday, April 27th. So I will post that on. That's technically the last class day. I will post that on Monday, April 27th at at 8:30 a.m. The usual class time, and then you will have until April the 29th, right, to return that to me. And then the homework number 7, which will be covered on that final test, but that will be optional for you to turn in. If you want to turn it in, you can turn that in to improve your homework grade. But if you don't want to turn in homework 7, you do not have to turn that in, so it won't count against you in your homework average. I will also be posting, I hope by this weekend, a sample test for our third test on April the 27th. We're going to talk about the last topic, which is on that third test. So that third test will include inclusion, exclusion, and then this topic, recurrence relations, which I'm going to start talking about today, and then I will follow up with in the 2 lectures for next week. We will not have a lecture on the final class day, April 27th, because that is when you'll be working on your last test. Now, another reminder for many of you, you may be satisfied with your test average, because many of you have a good test average. Going after test number 3, if you're satisfied with your test average, you do not have to take the final exam. So remember, you can replace the final exam score with your the average of your 3 midterms. All right, so you would not have to complete the final exam unless you just want to. But for others, if you're not happy with your test average, you would want to take the final exam in order to improve your test average, right? The final exam is scheduled for Monday, May the 4th, so we have to stick to that schedule. So I will be posting the final exam on Monday, May the 4th, and then it would be due back to me in the usual fashion by email on Monday, May the 6th, right? So are we sort of all understanding what the sequence of events is going to be, right? So homework 6 is due, I think, a week from Friday, April the 24th. And then homework number 7, which will be on recurrence relations, is optional, so you can turn it in if you want to improve your homework score, but it won't count against you if you do not turn it in. And then our final test, which will include inclusion, exclusion. It won't exclude inclusion, exclusion, right? Okay, it's going to include it. Sorry for the joke there. It's going to include it, and then it will also cover recurrence relations as well, right? So, and that will be on Monday, April 27th. So I'll send announcements about these things, of course, but just telling it to you, communicating this information to you verbally as well. Okay, so I hope everyone is doing fine and not going too stir crazy, waiting for the stay-at-home order to end. I'm sure, like me, you're hoping that will be soon, right? Okay, um, so you can get out of your house or apartment maybe a little bit more frequently. On the other hand, some of you may be essential workers, so you may have been working throughout this shutdown. Okay, if that's the case, then I definitely applaud you. Um, all right, so today I'm going to just start the lecture now. So today we're going to talk about recurrence relations. And so this is our last technique, obviously, that we use for counting a set, right? Finding the cardinality of a set. And we've actually already used recurrence relations for this purpose way back earlier in the semester in a couple of examples, which I'm going to remind you of here in just a moment of those examples. And so, but recurrence relations are useful sometimes when our more standard techniques like set models or algorithmic techniques do not apply. Okay, so there are many counting situations where set models and algorithms aren't really enough to help us count a set, and then that's where recurrence relations sometimes can be useful. All right, so we're going to look at just look at some examples of recurrence relations, and then next week we'll talk about using them maybe a little bit more closely. All right. So again, I didn't mention what is a recurrence relation anyway. So a recurrence relation is an equation that relates the cardinality of a set to the cardinality of smaller instances of the same set. Okay, so that's a very general definition that I just gave you there. It's kind of vague, so you need to see some examples. But that's what a recurrence relation is. Again, it's an equation, and what it does is it counts the size of a set based on the size of smaller instances of the same set. Now you might say, what do I mean by smaller instances of the same set? Well, usually when you're counting a set, right, you have some description of the set, right? Okay, and so a smaller instance of the set would be a set built from the same description, but which we know has fewer elements in it. Okay. All right, so let me give you again, we've already seen some examples, but let me remind you of some of the examples that we've already seen. And once you see an example, then it'll become clear what this definition of recurrence relation actually means. I think here's the first example, this example that I've got numbered 1 here in these notes. This example is the first example of recurrence relation that we saw back at the start of the semester. And this is actually a recurrent relation used to solve a problem in combinatorial geometry. So this is one of the examples of combinatorial geometry that we showed. And so remember this problem, this was in our notes. We have a certain number of lines, right? We're just going to call the number of lines n. N can be 0, by the way, but it's not negative, of course. So we have a certain number of lines, and they're drawn in the plane in general position. So remember, general position means the lines are not parallel to each other, so you don't have any parallel lines, and you don't have 3 lines that intersect in a single point. Of course, 2 non-parallel lines are going to intersect in some point, correct, right? But in this collection of lines, we don't have 3 of them that intersect all at the same point. Okay, so the question was, if you have this drawing, right, where you've got these n lines, right, drawn in the plane in general position, how many regions in the plane are going to be formed by the lines, right? How many distinct regions will those lines break the plane up into, right? Remember that problem? Probably you do, right? Back from the notes back in January or February, so it's been a while. All right, so here's the way I've edited it slightly, but here's essentially the way that we solved this problem. So we let L sub n denote that number of regions, okay, when we draw the n lines. Okay, so L sub n is the number of regions when we draw the n lines in general position. And I'm not going to repeat how we discovered this, the logic that we used, but we actually found that L sub n the number of lines when you draw, I'm sorry, the number of regions when you draw in lines was equal to L sub n minus 1. That's the number of regions when you draw one fewer lines, right? And then plus whatever n is, okay? This is an equation, obviously, and that's an example of a recurrence relation, right? Because that allows us to count the number of regions when we draw in lines, right? Based on the number of regions that were formed when we drew one fewer lines, right? When we drew n minus 1 lines, okay? So that's what I mean, counting a set based on a smaller instance of the set that's sort of defined in the similar way, right? Okay, so we knew that L sub n was equal to L sub n minus 1 plus, right? Of course, it's going to be more, so you have to add in this example, you have to add in, okay? All right, so you can look back and try to recall how we developed that recurrence relation. But that's the recurrence relation that we used to count this number of regions. Okay. All right. Now, how do we actually apply the recurrence relation to do the counting? Correct. Well, look, it's obvious here that L sub 0, that is the number of regions you get when you draw any lines, right? Okay, that is 1, because that the whole plane is just a single region, correct? So L sub 0 is equal to 1, and once you're armed with L sub 0, right, then you can start computing higher values of L, right? So L sub 1, that is the number of regions when one line is drawn. Well, obviously that's 2, correct? You know, geometrically you can see that easily in your mind, right? If you draw one line, it's going to break the plane up into 2 regions. But we can also get that from our recurrence relation, right? Because our recurrence relation says L sub 1 is going to be L sub 0 plus this subscript, right? Okay, plus 1. So L sub 0, though, is 1, right? We know that, and so you end up with 1 plus 1 is 2. Okay, which is, of course, what we knew it was going to be, right? So what's L sub 2? Well, that's going to be L sub 1 plus this subscript, right? Well, L sub 1, we just calculated that was 2, correct? The subscript is 2, so you get 2 plus 2 is 4. So when you draw 2 lines in general position in the plane, right, you get 4 regions. Again, you can just visualize that in your mind, and you can see that this answer is correct. 3 is much harder to visualize in your mind, okay, and count the regions. But fortunately, we don't have to visualize it, right, because we have this recurrence relation. So what does the recurrence relation say about L sub 3, the number of regions when we draw 3 lines? Well, let's see, it's going to be L sub 2, which we just calculated was 4, plus this subscript, right, which is 3, so we get 7. So try that. If you draw 3 lines in general position, it's going to break the plane up into 7 regions. What about L sub 4? Well, that's L sub 3, which is 7, plus the subscript 4, which is 11, and so forth, right? So see, we can use this recurrence relation to count L sub n for really any subscript, right, that we want. Of course, that's going to be a little bit tedious process, right? Because if you wanted to count, using this recurrence relation, if you wanted to count L100, right, well, according, that is how many regions you get if you draw 100 lines in the plane. Probably going to be a big number, right? But according to our recurrence relation, that's going to be L99, right, plus 100, right? Okay, L sub 99, the number of regions that you get when you draw 99 lines, right, plus this subscript 100. But see, of course, you don't know what this value is until you've computed L99, right? So then you have to compute L99, but to compute L99, you're going to have to compute L98, but to compute L98, you're going to have L97, right? So it's going to be kind of a tedious process to actually use the recurrence relate, although you can. A computer program would certainly help, right? It's going to be a tedious process to use this recurrence relation, right, to actually count, L for any given subscript. All right, so that being the case, we often like to take recurrence relations and we like to do what's called solving the recurrence relation. That is, take the recurrence relation and turn it into a non-recursive formula, okay? So is it possible for me to write down a formula for computing L sub n that does not involve me computing L sub n minus 1 first, right? Okay? Because, again, this formula being recursive makes it difficult to actually do calculations with in practice. Although you can, right? It works, but it's harder. It makes it hard to do calculations in practice. So actually, we were able to, as I recall, with a little bit of algebra, which again I'm not going to repeat because we've done this before, but with a little bit of algebra, we were able to analyze this recurrence relation, and we were able to actually solve the recurrence relation. That is, we were actually able to develop a formula for L sub n that was not recursive. It just depended on this subscript n, and here was the formula. It was n times n plus 1 over 2 plus 100, plus 1, not 100, okay, but plus 1. And so you see that non-recursive formula for L sub n, right, is a lot more useful for actually doing calculations. So we can calculate L100 would be easily here, that's 100 times 101, right, over 2 plus 1. So we get just 50 times 101 plus 1, whatever that number turns out to be. I think that's going to be, what, 5,051 if I'm doing that properly in my head, okay? So, so if you draw 100 lines in the plane, you're going to get from that 5,051 distinct regions in the plane. Is this correct? Yeah, I think that's correct. I don't know. If that's not correct, y'all can fix my arithmetic when you're watching this video. All right. So so there was our first example of using a recurrence relation to do counting, right? And also our first example of solving a recurrence relation. That is, taking the recurrence relation and then converting that back into a non-recursive formula, right? Okay, a formula for L sub n that does not depend on smaller values, right, of L. Okay. Now we actually had another example also earlier. This was not from the notes, but this was from the homework. Okay. And so this is from homework number 2. So I know you'll remember this problem because you probably spent a lot of time thinking about this problem. I know I did when I was working on the solutions to homework number 2. All right, so this problem was find the number of different perfect covers. We're covering with dominoes again, right, like we were earlier in the course. So find the number of different perfect covers of a 2 by n chessboard. So a chessboard with 2 rows in it, but any number of columns. You can obviously cover that by dominoes, because you could just arrange every domino vertically, right, and then cover every column with a domino. So so you certainly have at least one perfect cover, but actually you have lots of perfect covers of a 2 by n chessboard. And in this problem, we were trying to find out how many distinct perfect covers there are of a 2 by n chessboard with dominoes. And so in that problem, actually this was the one of the points of the problem. In that problem, we found that that number of perfect covers of a 2 by n chessboard. N is the variable here, so you can have different different number of columns, right, in the chessboard. That number of perfect covers, which we were calling F sub n. So F sub n is the number of perfect covers of a 2 by n chessboard, right? Of course, this n and this n are the same, right? So if we call that value F sub n, then it turns out that you can count F sub n using this recurrence relation. F sub n minus 1, that is the number of perfect covers when you have one fewer column in the chessboard, plus the number of perfect covers if you have 2 fewer columns in the chessboard. You add those two together, and that would give you that number of perfect covers when you have n columns in the chessboard. So see, there's again another example of a recurrence relation, right? Okay, that we were used to count a set. In this case, the set of perfect covers of this type of chessboard. Now, when you're using a recurrence relation, you usually have to know some of the small values of the size of your set. But we could, by inspection, we could easily see, right, that if the number of columns is 1, in other words, if we have a 2 by 1 chessboard, then you just have one perfect cover, because that 2 by 1 chessboard could be covered by just one vertical domino, and that's it, right? Okay. And it's also easy to see that if you have a 2 by 2 chessboard, there are two ways to cover that chessboard with dominoes. You can put the dominoes vertically, or you can put the dominoes horizontally. So f sub 2 is equal to 2. That we can just see by inspection. And once we've determined that f sub 1 is 1 and f sub 2 is 2, then we can use the recurrence relation to count higher values of f. So f sub 3 would be, that's going to be f sub 2 plus f sub 1, right? See, this is f sub 2 plus f sub 1, according to the recurrence relation, right? f3 would be equal to f of 3 minus 1, right? f2, and then plus f of 3 minus 1, right? 3 minus 2, which is 1, f sub 1. But we already know what f sub 2 and f sub 1 are, right? Because we discovered that just by inspection. So f sub 2 is 2 and f sub 1 is 1, so you get that f sub 3 is 2 plus 1, which is 3, right? And then, once you know what f sub 3 is, then you can calculate f sub 4, right? That's going to be f sub 3 plus f sub 2, so that's 3 plus 2, which is 5. And f sub 5 is going to be f sub 4 plus f sub 3, so that's going to be 5 plus 3, these two, right? Which is 8, and so on and so forth, right? So if you're patient, you can determine there that using the recurrence relation, you can determine the number of perfect covers, right, of this style of chessboard for any number of columns. But again, right, that's going to be, again, see, the hard thing is recurrence relations in practice, right, are kind of computationally tedious to use, right? If I wanted to compute f sub 100, right, I would need to know f sub 99, and I would also need to know f sub 98, right? And so then I'd have to work backwards and calculate f sub 99 and f sub 98, and then I'd have to work backwards and calculate f sub 98 and f sub 97, right? And so on and so forth. So that would take a long time, right? So although you can use the recurrence relation, right, to compute f for any subscript, it's tedious to use the recurrence relation. So again, what we want to do, if possible, with these recurrence relations is solve them. We would like to translate this recurrence relation formula into a formula for computing f sub n that doesn't depend on recursion, right? However, okay, this recurrence relation is not as easy to solve as the prior example, all right? So I'm not going to try to write down yet the solution for this recurrence relation. But we will study next week a little bit more about how you solve recurrence relations, okay? So how do you take a recurrence relation formula and turn it into a non-recursive formula for counting a set. Okay, this recurrence relation is actually a famous type of recurrence relation. This is called a Fibonacci recurrence relation. Okay, and this type of recurrence relation goes back a long way, believe it or not. Okay, this style of recurrence relation was actually first considered by the Italian mathematician Leonardo Fibonacci all the way back in 1202. Okay, so all the way back in the High Middle Ages, recurrence relations were already being studied as mechanisms for counting sets. Okay, so recurrence relations are definitely not a new idea in counting. He was, however, applying this recurrence relation to solve a different counting problem. Okay, so Fibonacci was not interested in covering chessboards with dominoes, although I imagine both the game of chess and the game of dominoes were known to Leonardo Fibonacci. That wasn't the problem he was trying to solve. He was trying to solve a different counting problem. But he also arrived at a recurrence relation very similar to that recurrence relation that we just looked at in this example. Fibonacci is actually an important figure in mathematics for things beyond recurrence relations. Fibonacci is really largely responsible for our current a system for representing numbers. So we represent numbers using a base 10 number system, correct? And using Arabic numerals, right? Arabic digits, 0, 1, 2, 3, 4, 9. Those are Arabic digits. And so Fibonacci was the person who really popularized representing number in Europe, representing numbers in base 10 with Arabic numerals. Okay, so he's an important person in actually in history, not just the history of mathematics, but history in general for that reason. All right, so those are examples that we have already looked at, right? So those are old examples to us. So let's take a look now at some new examples of recurrence relations that we're going to use to count sets. And we're going to start with a very simple counting problem that you already know how to solve with algorithmic techniques. But we're also going to solve the counting problem with a recurrence relation. All right, so we're going to start here with our favorite set, and that is the integer segment n, right? So remember, integer segment n, this is just 1, 2, 3, right, up to n, whatever positive integer there you select for n, right? You get a different integer segment, correct? And what we're trying to count here is the number of subsets of this integer segment, right? So the number of subsets of the set 1, 2, 3 up to n, right? Where n is just any positive integer. Okay, so I'm going to call that that collection of subsets, I'm going to call that S. So we're going to let S be the set of subsets of this integer segment n. So, if you write out a few elements of S, of course you can easily visualize what those look like, right? So what subsets do you have of this set? Well, there's always the empty set, correct? And every set is a subset of itself. So in the integer segment n, as a subset, you also get the integer segment n, correct? But then you have lots of other subsets as well, right? So you have like the set that just contains 1, right? Or the set that just contains 2, correct? Or etc., right? The set that just contains 3, or the set that just contains 4, all the way up to the set that just contains n. And then, of course, you've got 2-element subsets, right? So you might have 1 and 2, right? There's a 2-element subset, or you might have 1 and 3, right? There's another 2-element subset, and so on and so forth, right? Okay, so lots and lots of subsets, of course, of this integer segment n. Right? There's just a few of them, so we want to count those. And we already counted that earlier in the semester using algorithmic techniques, and well, we're going to say what that is again, but just recall the size of S ends up being 2 to the nth power, okay? So that was one of our first examples of using algorithmic methods for counting a set. We got that the number of subsets of this integer segment n, that turns out to be that number turns out to be 2 to the nth power. But so this is a formula for the size of S, but now we're going to develop a recurrence relation that will also give us the size of S. Okay, so let's let S sub n. Let's let that be our notation for the number of subsets of. I should have brackets on it. So the number of subsets of the integer segment n. In other words, I'm going to let S sub n be the cardinality of this set. So again, we already discovered that S sub n is going to be 2 to the nth power, okay? But again, I want to develop a recurrence relation for S sub n. All right, so here's the logic that we're going to use to develop this recurrence relation. So let's take the set S, right, this set of all these subsets, and I'm going to break it up into two disjoint partitions, A and B, right? So I'm going to break S into two pieces. This big set of subsets, I'm going to break that into two pieces, and the two pieces are going to be disjoint, so they're not going to overlap. So here's what they're going to be here, okay? I'm going to let A be the subsets that contain the number n, okay? So A is going to be the subsets that contain the number n. Remember, n is the largest number in your integer segment, correct? So I'm going to let A be all of the subsets that contain the number n. And then I'm going to let B be all the subsets that do not contain this largest number n. All right? So see clearly these two things are disjoint, right? A and B are disjoint because sets either contain the number n or they don't contain the number n, right? Can't be both, right? Okay, so a subset would either be a subset of your integer segment would either be in A or it would be in B, but it cannot be in both, right? Furthermore, every subset of this integer segment has to be in either A or B, right? Okay, so so A and B is a partition of the set S. So let's just make a note of that, right? So see, S is clearly equal to A union B, and A and B do not intersect, right? A and B do not intersect. Their intersection is the empty set. Because, again, this largest integer n, it's either going to be in a set or it's not going to be in a set, right? So you can't have a subset that's in both A and B, right? But every set either contains n or it doesn't. So if you take the union of A and B, that would give you all of S, right? So actually, now we can apply inclusion, exclusion, right? Okay, so because these two sets are disjoint, that means that the size of S is going to be the size of A plus the size of B minus the size of the intersection, right? But the intersection is empty, so you would just be subtracting off 0 here. So you see, if I can find the size of A and I can find the size of B, if I add those two together, I will get the size of S. But how big now is B? So how big is that, all of those subsets that do not contain the largest integer n? Well, look, the sets in B are going to be all the subsets of the integer segment in minus 1, right? Okay, if you take all of the subsets of the integer segment that doesn't include n, the largest number, that's going to give you a bunch of sets, right, that don't have n in them, okay? So B is really just, this set B is really just the set of all subsets of this integer segment. So again, let me repeat that. So the set of subsets, right, of this integer segment n that don't contain n, that's really all the subsets of the integer segment n minus 1, correct? But how big is that? Well, I don't know exactly, but in notational terms, I know that the size of B would be S sub n minus 1, right? Because that's the notation that I'm using for the number of all subsets, right, of this integer segment. So B is equal to S sub n minus 1. So I know what to put in here for B. This is S sub n minus 1, correct? Now, how big is A? Well, of course, A, remember the subsets in A, they do all contain the integer n. But it's easy to figure out how to find the subsets in A. All you do is take all of the sets in B that don't contain n, correct? And you throw in n, right? So in B, you have all the subsets that don't contain this largest number n, so just add this largest number n to all of those subsets, right? Okay, and that would give you all the sets that do contain this largest integer n. So guess what? A and B really have exactly the same size, right? Okay, because you can form a subset with the integer n by taking a subset out of B that doesn't contain the integer n and throw the integer n into it, right? Just add it in to the subset. So A and B really have the same size, but I already mentioned that's in our, the size of these two sets in our notation is s sub n minus 1. So so A is s sub n minus 1. So there you have it, right? The size of S, right? Which remember we're calling S sub n. That is 2 times S sub n minus 1. There is our recurrence relation. Okay. Nice, right? Okay. So we can count the number of subsets of the integer segment n by taking the number of subsets of the integer segment n minus 1 and just doubling that. Let's write out some values of this recurrence relation. Okay. Now, to start using the recurrence relation, you have to know some small values for s, right? But we know that s sub 0 is equal to 1. If you have a set with no elements in it, you have only one subset of that, right? That is the empty set, okay? So s sub 0 is equal to 1. That means s sub 1 is 2 times s sub 0, which is 2, right? Okay, 2 times 1 is 2. S sub 2 is 2 times s sub 1, so that's 2 times 2 is 4. S sub 3 is 2 times s sub 2, so that's 2. Whoops. No, I wrote that down wrong. Right, okay. That's 2 times s sub 2, but s sub 2 is 4, so you get 2 times 4 is 8, right? Okay. And so on and so forth, right? Okay, so so there is our recurrence relation version of solving the counting problem. How many subsets do we have of the integer segment n? But again, we had already solved that earlier in the semester using algorithmic methods, and we saw that the size of this set is 2 to the nth power, right? So there is the solution to our recurrence relation, right? Here's the non-recursive formula that we can use to calculate s sub n, right? Just take 2 and raise it to the nth power. Here's the recursive formula of how we can compute s sub n, right? Okay. So non-recursive, and then this is the recursive version. And again, one of our goals here, right, is to, once we have developed a recurrence relation, we want to make it non-recursive. We want to write down a non-recursive formula for that recurrence relation. Easier said than done, though. Okay, that's really the hard thing about using recurrence relations. All right. So I've got a couple more examples to show you here of recurrence relations, but let's pause here for a moment, okay, before we come back and look at those. Okay, so let's resume here with another counting problem, and we're going to develop a recurrence relation for this counting problem. So, and this is kind of a typical problem where recurrence relations would be applicable. So, what we want to do is count the number of bit strings. So that would be strings of zeros and ones, right? A bit is either a 0 or a 1. So we want to count the number of bit strings of length n greater than or equal to 1, but we only want bit strings that do not contain this 0, 0, 2 consecutive zeros. So this sounds like a problem that we might be able to solve through complements, right? Okay. but but we're going to develop a recurrence relation to solve it. Okay, so how are we going to set this up? So I'm going to let's let b sub n be this number of bit strings, right? That we're looking for. So the number of bit strings not containing of length n not containing 0, 0. Okay, so some small values of b, I think we can calculate easily, right? Because b sub 1, so that would be just a single bit, right? That doesn't contain 0, 0. Well, if you just have a single bit, right? Okay, that cannot contain a 0, 0, right? So this is going to be 2, correct, right? Because the only two bit strings of length 1, right, would be 0 and 1, correct? And neither one of those contain 0, 0, so that's easy. What about b sub 2 here? All right, so how many bit strings of length 2, right, do not contain 0, 0? Well, I think the answer to that is 3, because you only have 4 bit strings, right, of length 2 to begin with. You could have 0, 0, or, right, 0, 1, or 1, 0, or 1, 1, right? But, of course, 0, 0 contains 0, 0, right? This first bit string contains 0, 0, so that we would eliminate from consideration, and so that gives us 3 possibilities left, right? So b sub 2 there is equal to 3, all right? Now, let's see if we can find, right, now let's see if we can develop a general formula here, though, for b sub n. All right, so here's the logic that I'm going to use, right? So suppose you have a bit string of length n, okay? So that means I've got a lot of slots here that I have to fill in, right, with I've got a lot of slots here, right, that I have to fill in with zeros or ones, correct? So let's suppose that we start there, right, by filling in with a 1, okay? So suppose the first bit in my string is a 1. Right, but we don't want the string, remember, we don't want the string to contain 0, 0. Well, notice then what you're left with after you've put a 1 into the first slot is you're left with n minus 1 slots, correct? Okay, left to fill up. And since you had a 1 in the first place, right, that means you cannot, in these n minus 1 remaining slots, you cannot get a 0, 0, right? Okay, so basically, in filling up the last n minus 1 slots, correct? Basically, what you're doing is creating a bit string of n minus 1 bits, right? That don't contain 0, 0. Well, how many bit strings of n minus 1 of length n minus 1 don't contain 0, 0, right? Well, by definition, that is b sub n minus 1, correct, right? Okay. So if you start with a 1, right, then you have n minus 1 slots to fill up, but you can't put a 0, 0 in any of those n minus 1 slots. How many ways can you create a bit string with n minus 1 bits without a 0, 0? By definition, right, we're calling that b sub n minus 1. So a part of b sub n is going to be b sub n minus 1. But that's the case where we started the bit string with a, that's the case, right, that we started the bit string with a 1, right? Now, what happens though if we don't start the bit string with a 1? So suppose we start it with instead a 0. Okay. Well, if you start with a 0, that means the next bit has to be a 1 because you cannot have a 0, 0, right? So if you start with a 0, you know this next slot has to have a 1 in it, correct? But then that leaves you with now how many slots left to fill in? Well, that would leave you with these remaining n minus 2 slots, right? Okay, that you want to fill in with 1s and 0s. And how can you fill those in? You have to fill those in without putting in a 0, 0, correct? So basically what you're doing is you're creating a bit string with n minus 2 bits in it, right? That does not contain 0, 0. How many ways can you do that? By definition, that's going to be b sub n minus 2, right? Okay. Right, you're going to fill in n minus 2 bits. You can't put in a 0, 0 in those n minus 2 bits. How many ways can you do that? That is by definition b sub n minus 2. Oh, so there is our, cool, there is our recurrence formula, right? B sub n is b sub n minus 1 plus b sub n minus 2, right? Okay. Starting with these two values, b sub 1 is 2, right? And b sub 2 is 3. So now, for instance, you can calculate b sub 3, right? That's going to be b sub 2 plus b sub 1, but that is 3 plus 2, which is 5, right? Or b sub 4 is going to be b sub 3 plus b sub 2, but that is 5 plus 3, which is 8, right? Okay? Or b sub 5 is going to be b sub 4 plus b sub 3, which is 8, plus 5, which is 13, and so on and so forth, right? Okay, so you can continue to use that recurrence relation to compute b sub n for any value in there that you choose. Notice that this recurrence relation now is very similar to this recurrence relation is very similar to that recurrence relation for the number of perfect covers of a 2 by n chessboard, right? This is also a Fibonacci recurrence relation, okay? So here's another example showing up here of, again, what's known as a Fibonacci recurrence relation. Okay, all right, so now I've got one more example for you, okay? And we actually know the solution to this problem. Well, we're going to develop a recurrence relation, okay? And we actually know the solution to this recurrence relation for other reasons, okay? All right, so here's a problem that we considered in inclusion exclusion, right? So I think we did this at the end of the Monday's notes, okay? I'm going to let d sub n be the number of derangements of the integer segment n. Number of derangements of the intersection of the integer segment n. Remember, derangements means permutations where no number is in its natural position, right? Okay, no number is in its natural position. So a derangement is a permutation where you have the numbers completely mixed up, so to speak, right? No number is in its natural position. And so we studied that problem on in Monday's notes, and but now we're going to develop a recurrence relation for this number of derangements. And so here is the recurrence relation that we want to prove. So we want to show that d sub n is actually d sub n minus 1 plus d sub n minus 2, right? Okay, so it's kind of that Fibonacci style again, except we have this multiplier here in front, which is n minus 1. All right. By the way, do we know some of the small values for d? We do, of course, right? D sub 1 would be the number of derangements of 1. Right, okay, and that is 0 because if you only have a one element set, there's only one permutation of a one element set, and in that permutation everything's got to be in its correct position, right? So this is 0. But d sub 2, on the other hand, what does d sub 2 turn out to be, right? So remember, we want the number of derangements of the integer segment 2, right? So so what permutations are there of the integer? What permutations are there of the integer segment 2? Well, you can have 1, 2, right? Or you can have 2, 1. And that's it, right? Those are the only two permutations of the integer segment. The only two permutations of the integer segment 2. By the way, I think what notation did we use for that? That's p of 2, right? The number of permutations of the integer segment 2, and this is a derangement, but this is not correct. So there's 1 here. So d sub 2 is equal to 1. See, this is a derangement, right? Because the numbers are not in their correct order, right? None of the numbers are in their correct position. But of course, in this permutation, both numbers are in their correct position, right? So the number of derangements in case of with a subscript of 2 is 1, right? But we want to actually now leap and calculate the number of derangements of n objects, right? Okay, so we're going to use a logic kind of similar to this prior example. So when you're building a derangement, right, when you're building a derangement, you've got, of course, a bunch of slots to fill in, right, because you're building a permutation, right? So you've got these n slots that you have to fill in, but it has to be a derangement, right? It has to be a derangement. So you don't want any number in its correct, you do not want any number in its correct position, correct? So this means you cannot put the number 1 here, right? You cannot put the number 1 here. So what sort of things can you put here? Well, you can put 2, or you can put 3, or you can put 4, all the way up to n, right? You just cannot put the number of 1, the number 1 in the first slot. So it looks like we have n minus 1 choices to go into the first position in our derangement, right? Since we cannot put n 1. Okay, now what about what's going to go into the second position? All right, so let's think about what goes into the second position. Suppose we end up putting 1 in the, suppose we end up putting 1 there in the second position, okay? Then if that's the case, all right, then you just have these n minus 2. Well, let me back up here. All right, I'm going to make this. Let me make this a little bit easier. We do have n minus 1 choices, right, for the first slot, correct? Because we cannot put 1 here. But just to make this a little bit more concrete, let's suppose that we, of those n minus 1 choices, suppose we put 2 in the first one. So it could be 3 or 4 or 5, but suppose we put 2 here. All right. All right, so suppose I put 2, And then we'll analyze what happens when we put 3, or what happens when we put 4, etc. Right? So suppose I put 2 in the first slot, and then in the second slot, suppose that's where I put the 1. See, the 1 cannot go here. So suppose I put the 1 here, right? Then what's left, right, for these n minus 2 remaining slots? Okay, well, you're filling those up with 3, 4, 5, 6, right? Okay, etc. up to n. But you have to make sure you have a derangement, right? So none of those numbers 3, 4, 5, 6 up to n, none of those numbers can go in their natural position. So you can't put 3 here, you can't have 4 here, you can't have 5 here, up to, you cannot have n, right, in the last position. So basically what you're doing is you're in these last n minus 2 positions, you're deranging, right? You're going to be deranging the numbers 3, 4, 5, 6, etc. up to n. How many ways can you mix up? How many ways can you derange the numbers 3, 4, 5, 6 up to n? Well, we know that. That is d sub n minus 2, correct? Okay, that's d sub n minus 2. So if you start with 2 and then put a 1 here, then you have d sub n minus 2 ways of deranging the remaining n minus 2 numbers, correct, to make sure that they're not in their correct position. So you know the number of derangements is at least d sub n minus 2. Okay, but remember, that's the case. We started with 2, and then next we had 1, right? Now, suppose in the next place, right, we're not going to put the 1, right? Okay, so suppose we're not going to put 1 here. Then what we're, let's think about that. So 1 is not going to be in this second position. So we've got these n minus 1 slots to fill up, right? Notice this is now n minus 1 slots to fill up, right? If I'm not thinking about specifically putting 1 in this second spot, I've got n minus 1 slots to fill up, right? What numbers now are you filling up with the n minus 1? What numbers are you going to put into these n minus 1 slots? Well, you would put in the number 1's got to go in there somewhere, right? And then 3, and then 4, and then up to, etc. right here up to n. So you're putting those numbers in these last n minus 1 slots. But remember, you're doing that in such a way, right, that you do not get the number 1 in the first position, right? Because we've already considered the case 1 goes here, right? So basically what you're doing is you're mixing up, you're deranging this set. You want all these numbers out of their correct order, right? Okay, because you don't want 1 here. 1 is the smallest of these numbers, so its natural position would be here, right, amongst these numbers, but we were already assuming 1's not going to go here, right? So basically what we're doing is we're deranging this set, right, to fill up these n minus 1 slots. But how many ways can we derange this set? Okay, well, there's n minus 1, right? There's d sub n minus 1 derangements of this set. So thrown in here with the d sub n minus 2 is d sub n minus 1, correct? That's the possibility when 1 doesn't get in to the first position, and then none of these other numbers can be in their 3, 4, 5, etc. cannot be in their correct position either. Right. Okay. So if you start your derangement with 2, there are this many ways to complete the derangement. But remember, we could have started the derangement with not just 2. We could have started with 3. We could have started with 4, all the way up to n. And the same logic would apply in every case. So if you look at all the possibilities for starting here,
right? There are n minus 1 numbers other than 1. Remember, 1 cannot start in the first position in a derangement. So there are n minus 1 numbers you can start with. So that means altogether you take this sum and multiply it by n minus 1. Each time you change the starting number, you're going to get this many possible ways to complete the derangement. You're going to get this many possible ways to complete the derangement, right? But you have n minus 1 choices for this starting number other than 1. So there it is, okay? There's our recurrence relation for the number of derangements of the integer segment n. Remember now but we know the solution to this recurrence relation, strangely enough, because we know d sub n is, what was that? I think it was n factorial, right, times, what is that, 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus, etc., right, up to, and then at the end here, right, you would have either plus or minus, right, 1 over n factorial. I think that was our formula for the number of derangements. So there's the solution. Wow, that's a crazy solution, right? There's the solution for this recurrence relation. We can take this recurrence relation for the number of derangements and we can convert it into this non-recursive formula, but it's a kind of a bear of a non-recursive formula, right? But there it is. It was, this is easy to apply in practice, though, right? Okay, so there's another example of a recurrence relation. Let me see how we're doing for time here. Oh, okay. So I have enough time now to we're going to look at one last example, and that will be actually solving a recurrence relation. So I'll show you a simple technique for solving a recurrence relation. Let me pause here for a second, though, before we look at that. Okay, so let's look at just a last example here today quickly, and what we're going to do is actually solve a recurrence relation. So I'm going to give you a recurrence relation. I don't know what this is used for counting exactly, so don't know how this recurrence relation arose in practice, but I just want to take this recurrence relation and convert it to a non-recursive formula for computing S sub n, all right? So here's our recurrence relation. S sub n is equal to 2 times S sub n minus 1, and then we have 1 thrown in. Now, we do have to have an initial condition, however, so I need to know at least some of the small values for S, right? And so what we're given here is that S1 is equal to 1. So apparently in this recurrence relation, we do have to have n greater than or equal to 1, and we know that S1 is equal to 1. Okay, so that's a given. All right, so we're going to do this by just by some simple substitution, and this technique is, when it works, is easy to apply. So let me show you how we do this, right? So we know S sub n is 2 times S sub n plus 1, right? But see, because the relation is recurrent, right, then we can fill in for S sub n minus 1 what its value is, right? That should be 2 times S sub n minus 2 plus 1, correct, right? According to this recurrence relation, right? That's what the recurrence relation says. S of some subscript, right, is going to be 2 times S of the previous subscript, right, plus 1. So S sub n, which is 2 times S sub n minus 1, if you fill in for S sub n minus 1, right, you get 2 times S sub n minus 2 plus 1. Oops, and I forgot, don't forget to write in this 1 at the end, right? Okay, so I'm just substituting for S sub n minus 1 what its value must be according to the recurrence relation, which is 2 times s sub n minus 2, right? Now, if you expand that a little bit, you get 4, 2 times 2 is 4, right? 4 times s sub n minus 2 plus 2 plus 1. And I'm not going to add the 2 and the 1 together for reasons that will become clear in just a second, right? Okay. Now, however, I can keep substituting here, right? Because, right, what is s sub n minus 2 according to my recurrence relations? Well, remember, that's going to be s sub n minus 3, right? I'm sorry, 2 times s sub n minus 3, right? So s sub n minus 2 is 2 times s sub n minus 3 plus 1, right? So, see, I'm plugging in for s sub n minus 2 what its value must be according to the recurrence relation, right? Which is 2 times s sub n minus 3 plus 1. And then I have here, don't forget, this plus 2 and also this plus 1 are still hanging around, right? So now, when you expand this just a little bit, you get 8 times s sub n minus 3 plus 4 plus 2 plus 1. Now, well, let's just do this once more, okay? So, what's s sub n minus 3, right? What's s sub n minus 3? S sub n minus 3 is 2 times s sub n minus 4 plus 1, right? That's what s sub n minus 3 is, right? And so I have 8 times s sub n minus 3 plus 8 plus 4 plus 2 plus 1, right? Which simplifies to 16 s sub n minus 4 plus 8 plus 4 plus 2 plus 1. So now I think I see a, so we're going to continue here with, or imagine that we're going to continue here with this pattern of substitutions, right? So I'm going to substitute for s of n minus 4, and then I'm going to substitute s of n minus 5, and then I'm going to substitute s of n minus 6, right? And let's imagine once we've made all those substitutions, all the way till I get down to s sub 1, right? So I think we can imagine what's going to happen when we make all those substitutions all the way down to s sub 1, we're going to end up with the following. We're going to have that s sub n is equal to 2 to the n minus 1 times s sub 1 plus 2 to the n minus 2 plus 2 to the n minus 3 plus etc. here, all the way down to finally 2 and plus 2 squared plus 2 to the first power plus 2 to the 0th power here. 2 to the 0th power is 1, 2 to the first power is 2, of course 2 squared is 4, right? Okay, so if we keep doing these substitutions all the way down till we get here s sub 1, this is the pattern that we end up with, right? But remember, s sub 1 is 1. So now I can substitute in 1 for s sub 1. So I just get 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3 plus etc. here plus 2 cubed plus 2 squared plus 2 to the first power plus 2 to the 0th power, which is 1. And now, so there actually is the non-recursive formula for S sub n, but that's pretty messy, right? But actually, it turns out that you can simplify this big sum, 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3, etc., all the way down to 2. And it turns out you can simplify that, and that turns out to be just 2 to the nth power minus 1. Okay, so this big sum simplifies to 2 to the nth power minus 1. I was going to show you guys that, why the sum of all these powers of 2 just turns out to be 2 to the nth power minus 1, but that's a pretty easy thing to demonstrate, but I think we're out of time here, right? So let's check. Yeah, we're out of time, so I'm not going to be able to show you that today. All right, so there's our introduction to recurrence relations. And so we're going to talk more next week about actually solving recurrence relations. What techniques can we use to take, again, these recurrence relations and convert them to non-recursive formulas. All right, guys, so sorry for the delay on this week's Wednesday lecture. I hope to avoid that next week, and you guys take care, as always. As I always remind you, right, wash your hands and wear your face mask. I think face masks will help, so wear a face mask when you're out in a crowd, right? And I will see you guys next week. Bye-bye.